to our last speaker, Madalyn.
Hi, so yeah, my name is Madalyn, and I'm also going over our thermocouple time constant data, and I'm part of group 3. So our experiment objectives was to determine the time constant of a thermocouple using our temperature measurements, and then we compared the thermocouple response for heat addition and then heat removal. So as far as what is a time constant, it just kind of represents how quickly a system responds to a sudden change, but physically it's kind of showing like a balance between thermal mass and heat transfer rate. So a larger time constant, the temperature changes really slowly. It's a weaker convection, and then a smaller time constant, the temperature changes very quickly, so a stronger convection. And the way that we can change that time constant is like if we alter the thermal mass. So if we change the material of our thermocouple, it would increase the density, so we would have a larger time constant. And then if we were to change our convection, so like if we were to put a fan on the thermocouple, that would increase our convection, so we would have a smaller time constant, so the temperature would change more quickly. The materials we used: type K thermocouple, PDAC acquisition system, boiling water bath, ambient air, and then I did my data analysis in MATLAB. So for assumptions, we first used the lump capacitance assumption, which means that the internal temperature gradients are negligible, and then we can justify treating it as a first order system. Also, with our constant convection coefficient, we can just assume that while the thermocouple's in the water, the temperature is constant. When it's in ambient air, the temperature is constant. And then for the step change, we can assume that like whenever we put it in the water, we're ignoring that that time where it's like going down like into the beaker, and so we just see it like suddenly exposed to a new surrounding temperature. So our governing equations, the first one's that lump capacitance method, and then if we integrate it, we can get the first order differential form, and then we can normalize the response, and then we can do the natural log linear form, which is where we get that straight line of the data. So then we can see that our time constant is equal to the negative reciprocal of the slope from the natural log linear form. So how we collected the data was we connected the thermocouple to our data acquisition system, then we put the thermocouple into the water bath and recorded the temperature versus time until steady state is reached, and then we removed the thermocouple from the water bath and we dried it off, and drying it off just removes the water from the thermocouple, so we don't get any like excess evaporation, which can skew our data. And then we held the thermocouple in ambient air, and then we exported that data and processed it in MATLAB. So this is my raw temperature plots. During insertion, the temperature increased rapidly and then gradually approached the water, and then that's at the top. And then on the bottom, we can see that the removal plot's like a much slower temperature change once it's exposed to the air. And so even like from these plots, you can already start to see that whenever we're doing the heat addition, it's like a much steeper slope than the removal. Then we normalized this data. So on addition, the normalized temperature drops very quickly, so we can see that the thermocouple is responding very fast. And then during removal, the temperature decreases much slower. You can see it's like over a significantly longer amount of time. And it's also, whenever we normalize it, we keep the data between like 1 and 0. So then for our time versus natural log, we applied a linear fit to the region. So I looked to see where the normalized data was between, I chose to do it between 0.9 and 0.1. I only used the data points that really like highlighted that linear fit, so that's why I only have 3 data points on the heat addition graph. So I had, for my removal, I had a time constant of 60, and then for my addition, I had a time constant of 1.4. So for our discussion, why is the time constant much larger during removal? Removal happens in air, where heat transfer is much slower, so that's leading to a larger time constant. And then why is insertion and removal of responses differ? So it is a similar trend, it's just, like I said, the removal stretched out over like a longer period of time. And then y is only part of the data used to determine the time constant. So I know whenever we use that natural log form, once it approaches 0, the data can kind of get skewed and just disrupt the whole like representation when we're trying to calculate our time constant. So like I said, that's why I chose to use the like 0.1 to 0.9 bounds. And I have the references.
Can we give a round of applause to Madalyn? Anybody have any questions?
Why do you use MATLAB instead of Excel?
I just prefer MATLAB, honestly. I just never like really was forced to use Excel, so I don't really use Excel.
All right, can we give everyone one round of applause? All right,